You know, everything around us, everything that makes us who we are, it's all just made of these tiny, tiny things called atoms. And they're constantly moving, constantly interacting in this intricate dance. So what if you could actually see that? Not just imagine it, but watch it happen in real time. Well, today we're going to dive into exactly that, the incredible virtual microscope that lets us watch atoms in motion. Okay, so here is the big puzzle, right? How on earth do you watch something that moves way, way faster than we can see and is literally smaller than the light you would need to see it with? I mean, it sounds completely impossible. How do you even begin to tackle a problem like that?
All right, so here's our game plan. We'll start with what it means to watch atoms move, then look at the engine that makes it all happen. We'll check out the rulebook that governs these simulations, peek inside that rulebook, and finally see how it's all put to work. Sound good? Let's jump in.
Okay, first up, watching atoms in motion. So back to that question, how do you see the unseeable? Well, the answer isn't a better microscope or a bigger lens. It's actually something completely different, something built inside a computer.
The tool is called molecular dynamics, or you'll just hear it called MD. And honestly, the best way to think about it is as a movie, an atomic movie. It's a computer simulation that creates a film of what atoms and molecules are actually doing in real life. It lets us see how they move, how they interact, how a protein folds. You get the picture. It's our virtual camera into this invisible world.
So, Section 2, the simulation's driving force. I mean, an atomic movie sounds absolutely incredible, right? But how does a computer know what an atom is supposed to do? What's the engine making this whole thing run? You might think it's some super complicated, modern physics, but it all comes back to something you probably learned in high school. The entire simulation, all of its amazing complexity, is built on one simple, elegant idea: Newton's second law.
Yep, good old F equals ma. Force equals mass times acceleration. It seems way too simple to power something this complex, doesn't it? But that's the beauty of it. This one equation is the absolute engine of the whole simulation. Think about it. If the computer knows all the forces pushing and pulling on an atom, the F, and it knows the atom's mass, the m, then it can perfectly calculate its acceleration, the a. And once you know how it's accelerating, you know exactly where it's going to be a split second later.
So this is how it works in practice. It's basically a loop that repeats over and over. You start with your atoms in some initial positions. Then for every single atom, the computer calculates all the forces acting on it. Step 3, it plugs those forces into F equals ma to figure out how each atom will move. Then it nudges every atom to its new spot. And finally, it just does it again and again and again. Millions, even billions of times, taking these tiny little time steps to build up that smooth, continuous movie.
Okay, but this brings us to the million-dollar question, right? We can calculate the movement if we know the forces, but how in the world does a computer know the forces between atoms? Like, how does it know how a carbon atom and an oxygen atom are supposed to interact? Where do those rules come from? Section 3, Force Fields, the rulebook. And the answer to that question is something called a force field. Now, it's not a sci-fi energy shield or anything like that. A better way to think of it is as the rulebook for the atoms. It's the instruction manual that tells the computer exactly how every atom should behave.
So, what is a force field, really? Under the hood, it's basically a bunch of math, a set of functions and numbers that describe the energy and forces between atoms. It's the physics engine for our simulation. And here's the really clever bit. It's what we call a classical approximation. It doesn't get bogged down in all the super complex quantum mechanics. This is a huge deal, because it means the calculations are fast enough for computers to actually handle. We trade a tiny bit of perfect accuracy for the power to simulate millions of atoms at a time. It's a brilliant trade-off.
And this is super important. It's not a one-size-fits-all situation. There isn't just one rulebook. Scientists have created lots of different force fields, like Amber, Charm, Gromos. Each one is like a specialized tool. It's been fine-tuned to work best for certain types of molecules. So picking the right force field is a huge part of setting up a good simulation.
So just to give you a feel for it, look at this. You've got Amber, which is the go-to for things like proteins and DNA. Then there's Charm from Harvard, which is a great all-arounder for biomolecules. And then you've got something like MMFF from Merck, which is built specifically for small organic molecules, the kind you find in drugs. So you see, you really have to pick the right tool for the job. Okay, so we've got this idea of a rule book. Let's actually pop the hood and take a look inside. What are the main rules in this thing? At its heart, it really boils down to this one simple idea.
The total energy of the whole system is just the sum of two kinds of energy, the bonded parts and the non-bonded parts. So what does that actually mean?
It's actually pretty intuitive. On one hand, you have bonded interactions. This is for atoms that are actually stuck together with chemical bonds. The analogy here is perfect. Think of them as being connected by little springs. They can stretch, they can bend, they can wiggle. Then you have the non-bonded interactions. This is for atoms that are just floating near each other, not directly connected. Think of these like tiny little magnets that can attract or repel each other from a distance. The force field has rules for both.
All right, last section, putting the simulation to work. We've got our physics engine, F equals ma. We've got our rule book, the force field. So how do we actually, run the thing? How do we put it all to work and actually see something?
Well, you need the right software. The first piece is the workhorse, the giant calculator. A program like NAMD, which stands for Nanoscale Molecular Dynamics. This is the beast that does all the heavy lifting. It takes the rules from the force field and just calculates over and over. It's built for parallel computing because, trust me, doing this for millions of atoms is a huge amount of work. But a bunch of numbers flying by on a screen isn't very useful, is it? You need to see what's happening. That's where the second piece of software comes in, something like VMD, Visual Molecular Dynamics. If NAMD is the engine doing the work, VMD is the camera. It's the visualization tool that takes all that raw data and turns it into those amazing interactive 3D movies of our atoms dancing around. This is how we actually watch and analyze the simulation.
And the sheer scale we're talking about here is just mind-blowing. Modern simulations, using tools like these on supercomputers, can handle systems with over 1 million atoms. We're not just looking at a few molecules anymore. We're talking about simulating huge, complex biological machines, things like an entire virus. It's absolutely incredible. So the big question, why does this all matter? What's the point? Well, this virtual microscope is a total game changer for science. If you want to design a new drug, you can literally watch it dock with a protein to see how it works. If you want to create a new material, you can test its properties on the computer first. It lets us understand diseases at the most basic level and figure out what our lab experiments are actually telling us. It's a huge deal. So we started with what seemed like an impossible question. How do you see something you can't see? And we ended up with this incredible tool that lets us watch the fundamental dance of life itself. It really just leaves you wondering, right? Now that we have this power to see how things really work at the atomic level, what's the next big mystery we're going to solve?